Today we want to get into the next big thing, and that would be solving oblique triangles. This is just a variation on solving right triangles, only one of the angles is not 90 degrees. We're taking that piece of information away and installing another piece of information in it. The great thing about solving oblique triangles is that these same techniques can be used to solve right triangles. So it's backwards compatible. All your PS3 games will work perfectly fine in your PS4. I don't even know if that's true. But it is backwards compatible. So we're really just expanding stuff that we already know. So let's remind ourselves of what we already know. So recall the solving triangles game. In the solving triangles game, you're given 3 pieces of information about a triangle and then asked to find the other 3. Given 3, find 3. That's the solving triangles game. Given 3, find 3. In the right triangles game, one of the given pieces of information is a 90-degree angle. When solving right triangles, one of the pieces of given information is a 90-degree angle. When solving right triangles, one of the givens is a 90-degree angle. Because of this, we had a specialized tool set for dealing with right triangles. Because one of the angles is a 90-degree angle, we have a hypotenuse, and that means we can use sine and cosine and tangent because we have opposite, adjacent, and hypotenuse. So our tool sets if you recall, our tool set for solving right triangles was the sum of the angles is 180 degrees. That's going to apply in oblique triangles as well, because that's just always. So the tools that we had are the sum of the angles is 180 degrees. One of the specialized tools that we have for right triangles, so this is an any triangle tool. One of the specialized tools that we have for right triangles is the Pythagorean Theorem. This is a right triangle tool. And we had our trig ratios. This is also a right triangle tool. Mainly it involves the 2 big ones, sine and cosine, involve the hypotenuse, and that means we need a right triangle. If we need a hypotenuse, we need a right triangle. But we have the trig ratios. Sine theta is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. I was already thinking of tangent. Now I spelled A wrong. I just spelled A as D. All you A students should be worried. Cosine of theta is adjacent over hypotenuse, and tangent of theta is opposite over adjacent. Tangent doesn't have hypotenuse in it, but it is talking about opposite and adjacent, and those should remind us that we need a hypotenuse for these trig ratios to work. So these trig ratios are also a right triangle tool. So we need to develop a tool set that does not require a right angle. Right now, all we have is the sum of the angles is 180 degrees. The Pythagorean theorem and our trig ratios are for right triangles only. And the game that we want to play now is solving oblique triangles, which means we're not going to have a 90-degree angle. Any questions before we start developing our tool set? Visually, what we're doing is switching from a right triangle, where one of the things that we're given is definitely a right angle, so really what we got in solving in the solving right triangles game was a right angle plus 2 additional pieces of information. And now we want to solve an oblique triangle. So now we're just going to be looking at a triangle where we don't have a right angle. Oops. Doesn't necessarily have to be obtuse like this one is. We just have no right angle. So what we need are tools for oblique triangles. Yes, if you have an oblique triangle, you can always drop down a line perpendicular. So for like this oblique triangle, if I pick this obtuse angle, if I drop a perpendicular line to the side opposite, I can create 2 right triangles. So I could ask you these questions without developing a new tool set. There are workarounds, but we want more generalized tools. So we need tools that work on any triangle. So that's actually a great observation, and an observation that I always forget to make when I go into this. You can turn any triangle into a bunch of right triangles and solve from there. So, and also, the best tool to use is the one that you have right in front of you. It's like the best guitar that you have is the one that's available for you to play. So the guitar that you want that's off in some other country somewhere that you can't afford, that's not a very good guitar because it's not available for you to play. So the best tool to use is the one that you have, that you can make work. But we'll still be better off if we have a bigger tool set. So we want to develop more tools that'll work on any triangle. And what we're going to start with, the first one that I like to start with is called the law of cosines. The reason I like to start with this is that the law of cosines is a generalized Pythagorean theorem. It's like a Pythagorean theorem, but for any triangle. It also sounds very authoritative because it's the law of cosines. So the law of cosines is a generalized Pythagorean theorem. The Pythagorean theorem requires a right triangle because we talk about the hypotenuse. There's a hypotenuse, there's got to be a right angle. If we don't have a right angle, don't have a hypotenuse. Can't use the Pythagorean theorem. So the law of cosine steps in and is a generalized Pythagorean theorem. The great thing about the law of cosines is that if we have a right triangle, the law of cosines still applies. The Pythagorean theorem is contained in the law of cosines. That's what I mean when I say it's the generalized Pythagorean theorem. So the law of cosines contains the Pythagorean theorem. If we had instead of started with the Pythagorean theorem back when you learned Pythagorean theorem, if we had just led with this, then when the Pythagorean theorem came up, everybody was like, oh yes, of course. This is just a special case of the law of cosines. So we should learn the generalized forms of things. We're going to start with our usual triangle. Consider a triangle with sides A, B, and C opposite angles alpha, beta, and gamma, respectively. Is this E supposed to be there? Yeah, that E is there, right? 3 E's or 2. This is one of those words that just never looks correct to me. Without the E, it looks wrong. This looks wrong, wrong, wrong. One of them is right, I'm hoping. So alpha is opposite A, beta is opposite C, or opposite B, gamma is opposite C. Our usual. So the thing that's changed, instead of A, B, and C, where C is the hypotenuse and gamma was a 90-degree angle, gamma is now just going to be any angle. Here's what the law of cosine. Here's the law of cosines. There are going to be 3 versions, which is actually 6 versions, but there are going to be 3 different versions of the law of cosines. C squared is A squared plus B squared. Now at this point you're thinking, hang on, Leach, this looks like the Pythagorean theorem. And it does. But the law of cosines has another term in it. A squared plus B squared minus 2AB cosine of gamma. There's the extra term for the law of cosines. C squared is A squared plus B squared minus 2AB cosine of gamma. Notice that if gamma is 90 degrees, then the cosine of 90 is equal to 0, And so this term drops out, and we get the Pythagorean theorem. So that's super cool. It's the Pythagorean theorem for non-right triangles. And all we need is this extra term, minus 2ab cosine of gamma. However, this raises an important question. Right now, you're looking at alpha and beta and saying, where's alpha and beta? But like I said, there are 3 versions of the law of cosines. I always lead with the c squared equals a squared plus b squared minus 2ab cosine gamma, because then the gamma, when gamma is 90, we drop out this cosine term and we get the Pythagorean theorem. But there are other variations. We usually call C the hypotenuse, but there's no reason that B couldn't be the hypotenuse. So one of the other versions of the law of cosine says that B squared is a squared plus c squared minus 2ac cosine beta. Just switch the B and the C, switch beta and gamma. So it seems like a lot to remember, but if we see the pattern, it's not that much. It's one extra term and then permutations. Then the last one, there's one for a squared as well. And now I'm just going to switch the a and the b. B squared plus c squared minus 2bc cosine alpha. So the first step is to learn the law of cosines, these 3 versions of the law of cosines. You can do that by memorizing these 3 things separately. Sometimes I like to make my life difficult too. Or you can focus on this first one and notice and look at the form of the extra term that we need to generalize the Pythagorean theorem. And that gamma is the 90-degree angle. If that gamma is the 90-degree angle, then we get the Pythagorean theorem. Then we got the a squared plus b squared equals c squared. And then just start saying, well, what if b is the hypotenuse? Then b squared is equals a squared plus c squared, and there's the term when beta is 90 degrees. Or there's the term when beta isn't 90 degrees. And then do the same thing for a squared. Look for the patterns to see how things are related. Then you don't have to remember so many things. That's stage 1. Remember these. Best way to learn law of sines is to just open up the book to the law of cosines, or law of cosine sections, and start solving problems. Step 2, we got to learn how to use the law of cosines, what we can use it for, and then how we can use it. We can use the law of cosines to solve for sides or solve for angles. We can use the law of cosines to solve for a side and solve for an angle. So what we're going to do is take the base form, c squared is equal to a squared plus b squared minus 2ab times the cosine of gamma. And I can use this to solve for side c or angle gamma. So I can solve for side c. C by just taking the square root of the stuff on the right side. So C is the square root of a squared plus b squared minus 2ab cosine of gamma. We can also use this form of the law of cosines to solve for angle gamma. So I have all this stuff happening to the gamma, and we can see that gamma is inside of a cosine, so we're going to have to do a cosine inverse. So let's get the cosine of gamma all by itself. So we can also use this to solve for angle gamma. So first, I'm going to get the cosine of gamma by itself. So I'm going to have minus 2a. I'm going to have to do a little bit of algebra. Sorry about that. I'm going to subtract a squared and b squared from the c squared side. Then we're going to divide by a negative 2ab. Now we're going to look at this fraction that we have over here on the right and say, ugh, dividing by negative 2ab, this looks terrible. So I'm going to fix this negative 2ab. I'm going to change all the signs. This is perfectly fine, but it looks terrible. So if you're looking at this right now and you're thinking, no, I'm kind of neutral on that, it's fine, dividing by negative 2ab. I need to poison your mind right now and say, no, this looks terrible. And you're like, oh, well, it does. And everybody's like, oh, yeah, this looks bad. It's kind of like how bands become super picked on. Right? So one day you're just like sitting there and you're just listening to some Nickelback. It's like, oh, all right, this is, listening to Nickelback. This is cool. Everything's fine. Then you hear everybody say, oh, no, Nickelback is bad. You're like, oh, it's bad? Okay, I better stop listening to this. Or I'll only listen to it in my car with the windows rolled up. You know what I'm talking about? I'm not a Nickelback fan, but I think they get a lot more crap than they've earned. I mean, seriously, it's just a band. So what we're going to do is we're going to fix this negative problem, even though it's not really a problem. And we're going to multiply by 1. So I'm going to multiply by negative 1 on top and a negative 1 on the bottom so that I can rewrite this as cosine gamma is a squared plus b squared minus c squared. Just changing all the signs so I can have this positive 2ab on the bottom. And then we'll be like, oh, that looks better. And so that gamma will be just the cosine inverse of this fraction. So gamma is cosine inverse of a squared plus b squared minus c squared over 2ab. So I can use this version of the law of cosines to solve for side c with a square root, or solve for angle gamma with a cosine inverse after a little bit of algebraic sleight of hand. We also have to remember that the law of cosines has 3 variations. And so I could also use a different law of cosines to solve for side B and a different law of cosines to solve for side A. So we also got to get our variations. So we'll also have B is equal to the square root. I'm just going to do a permutation on the one I have above it. A squared plus C squared minus 2AC cosine beta. And the variation for side A will be the square root. Now I'm just going to switch the A and the B of B squared plus C squared minus 2BC times the cosine of alpha. We can also do the same permutation trick on angle gamma by trading angle gamma for angle beta. So beta will be the cosine inverse of, let's see, all the C's are going to become B's, and all the B's are going to become C's because I switched from gamma, which is a C angle, to beta, which is a B angle. So I'll have A squared plus C squared minus B squared over 2AC then I'll check very carefully to see if I permuted everything correctly, and I think I did. And then, of course, we have the alpha variant. This cosine inverse of, now the A and the B are going to have to switch. So I'm going to have B squared plus C squared minus A squared over these two, 2BC. Now, we could take these 9 things that we've written down and think of it as 9 different things and just start memorizing 9 different things. But that would be missing the point. We want to take the first one, C squared is equal to A squared plus B squared, which is a variation of the Pythagorean theorem that we know. And remember what the form of this extra term looks like, minus 2AB cosine of gamma. And then just permute it to the variations. If we look at our law of cosines, we look at how things are paired. We have the first one is the C and the gamma, the B and the beta, A and the alpha. And whatever angle we have in the law of cosines, the opposite side only appears one time. And then the other 2 sides appear a couple of times. So if you have the cosine alpha version, that's the A squared version. So it's going to be a B squared, a C squared, and a minus 2BC. The beta version is the B squared version. That's the A, the C, minus 2AC. So look for those kind of connections and look for those kinds of patterns, and it'll make it easier to remember the law of cosines. When I used to give in-person tests with trigonometry, if I allowed a page of notes, the most tragic thing that was written on any page of notes was all 6 of these. When you write all 6 of these on your page of notes, then you're just trying to program yourself. And you're doing yourself harm for learning, for training the way that math wants to train you. It's like going to the gym and doing the exercises wrong. It'd be like going to the gym and doing an exercise in a way that makes the exercise easier to complete, but defeats the purpose of the exercise. Like, see people doing bicep curls with a lot of motion in them. So if you're swinging your arms to do bicep curls, you're doing yourself harm. Not necessarily because you're going to get hurt, but you're using the momentum and the swinging to try to lift to lift the barbell up or the dumbbell up or whatever you happen to be lifting. I don't know. I don't go to the gym. But that defeats the purpose. You're supposed to be using your bicep muscles to lift the thing up. By trying to use the momentum, by trying to leverage the momentum and use that to help you, you defeat the purpose. By writing all 6 of these things down, you lose the point of seeing the connection. You lose a piece of the connection between how they're all related. And it makes each one of them harder. So the more that you rely on all 6 of them being written down in one place, the more you're going to need that. You're developing a dependence upon remembering these formulas. Another analogy I like to use that does not involve the gym, mainly because I try to avoid the gym at all costs, is when people write down the slope formula. If you write down the slope formula on your notes and you write down m equals y2 minus y1 over x2 minus x1, you do not understand the slope. And that is the first piece of evidence I'll pull out. So I go, this person claims to understand the slope, but they're just imitating because they need y2 minus y1 over x2 minus x1. They don't understand what the slope is supposed to say. They don't understand the slope of the change in y over the change in x, the rise over the run. They know all those words, but they're not actualizing those words. They're not internalizing those words because they're relying on the formulas. So let's talk about how we can use this, what kind of information we can be given. Notice that if we want to use the law of cosines to solve for an angle, we need 3 sides. If I want to solve for alpha using the law of cosines, I need side A, side B, and side C. So notice, to use the law of cosines, to solve for an angle, we need all 3 sides. Looking at the form of alpha, beta, and gamma, if I want to solve for an angle using the law of cosines, I need to know all 3 sides. Every formula for alpha, beta, and gamma is some combination of all 3 sides, A, B, and C, A, B, and C, A, B, and C. To use the law of cosines to solve for an angle, we need all 3 sides. To use the law of cosines to solve for a side, let's just look at the forms over here. To use the law of cosines, to solve for a side, if I want to solve for A, I need to know angle alpha. I need the angle opposite the side that we're looking for and the other 2 sides. Well, that's pretty wordy. To use the law of cosines to solve for a side, we need the angle opposite the side we're looking for, plus the other 2 sides. We want a better way to phrase that. So let's draw a picture. So if I want to solve for angle alpha, or sorry, if I want to solve for side A, I need side B and side C, the other two sides, and angle alpha, the angle opposite the side that we're looking for. So what we need is side B, side C, and angle alpha to solve for A. To solve for side B, I need side A and C. To solve for side B, I need side A and C, and the angle in between A and C, which is beta, the angle opposite B. To solve for side C, using the law of cosines, I need angle gamma and the sides A and B. So to solve for a side using the law of cosines, I need two angles and the included two sides. Sorry, I just pointed to sides and called them angles. Two sides and the angle between those two sides. So we'll say two sides and the included angle. So to use the law of cosines, to solve for a side, we need two sides and the included angle. So I need a side, the angle in between, and then the other side. So I need a side, an angle, and a side. So I encode the two sides and the included angle by writing two sides and an angle in between them. So I put SAS for side, angle, side. That's two sides and the angle in between those sides, the included angle. So for all three sides, we can call that SSS. We can also use the law of cosines. So I could use c squared is a squared plus b squared minus 2ab cosine of gamma. I can also use that to solve for a squared or solve for a or b, but the equation comes out quadratic. Let's avoid that if we can. To be completely predictable, we talked about the law of cosines today. So you should probably suppose that there's going to be some other law that will cover not these cases. All right. We are out of time. That's going to do it for today. I want you to, first step, learn your law of cosines. And next step, that includes all the variations, not by memorizing, but be able to derive these from what you know. And then learn when we can use the law of cosines to solve for an angle or to solve for a side. And then come up with some situations where we can't use the law of cosines. Or the law of cosines would just be cumbersome. All right. That's going to do it for today. I will see you all on, oh, it's Wednesday. That's it for this week. I'll see y'all on Monday. Everybody have a great weekend, and thanks for playing.